Okay, so we're going to talk a little bit about a very brief mathematical view of PCA, mainly focusing on the concepts. So one way that you can view PCA is through something called the singular value decomposition, or the SVD, specifically when the data is centered. And so if you have so this formula here is just what the SVD is. And if we kind of label what these are, so you imagine that this X matrix is your data, and we'll say that the dimensions of that are n rows by m columns, they'll decompose into these three other matrices, U, sigma, and W. And so for this case, we're just going to label them as U being the left singular vectors, the sigma matrix being the singular values, and the W being the right singular values. And so the dimensions of these are n by k by k for the sigma, and m by k for the right singular values. And if you kind of apply what you've learned about matrix multiplication, you'll see that the dimensions ultimately match between the two sides of the equation. And so here we also introduced the new notation of this k. So that k is actually how many principal components you wish to look at. So in the cases we've been looking at one or two PCs, and that's often useful for visualization. But if you have data that's much higher dimensional, you can pull out more PCs. So in this kind of formulation, we've talked about things like the principal components, the PC scores. So in this formulation, we've actually seen some of these things. So it's this W matrix that actually captures these principal components, and the product of this U and sigma that gives us the PC scores. But we're going to introduce something new. So this new term is called the loadings. And so that is that sigma matrix in the middle times that W matrix. And what the loadings are is that they give you an idea of how to interpret each column and how they contribute to each PC. And so that sigma matrix used to have like some sort of special properties, right? So in the singular value decomposition, the sigma is always a diagonal matrix. And what that means is that every entry off the diagonal is a 0. So in this case, you can see on the diagonal, starting in the top left corner and just kind of moving diagonally to the other corner, there are values there, but every other position is 0. And one thing that's special about this is that it tells us about the amount of variation or information that each PC contains. So one thing that people are often interested with principal components is the amount of percent variance that can be explained by each PC. And that's given by this formula, where you take the square of the singular value from this matrix, and you divide it by the sum of each square. So in this case, if we were interested in how much variation that the first PC explains, we'll take that 3 from the first position, we'll square it, and then we'll divide it over the sum of each of those squares. So in this case, since we have 3 elements, it would be 3 squared plus 2 squared plus 1 squared.